Hello, everybody. Welcome again to our webinars. Today, we have the pleasure to listen to Giuliano Giacalone. Giuliano is theoretician, initially working on high-energy physics. He did his thesis at GdR RESANET, and he ended it in 2020. And already in his thesis, he started to look at the interface between high energy and low energy nuclear physics in theory. Then since 3 years, he's postdoc at the University of Heidelberg at the Institute for Theoretical Physics. And there he's also studying this interface between low energy and high energy nuclear theoretical nuclear physics. He received for his thesis work. He got the prize of the Nuclear Physics Division from the European Physical Society. And yeah, so that's all for the introduction. So Giuliano, thanks again. And now we listen to you.
Okay, thank you very much. It's a great honor to be invited to give this talk, and it's a great pleasure. So the topic of this talk, as was introduced, is work at the interface of low energy nuclear structure and high energy nuclear collisions, and all the progress that we've made there. So just to give you then an idea of the context of this research, these are all events that have been organized in the past couple of years, essentially on the subject. There's quite a broad community effort that has been devoted to understanding better how to connect low energy nuclear structure and high energy avion collisions. We had, for instance, a 5-week INT program last year, which was really great. There will be another program gathering the two communities next year in Beijing. So this is, I think it's fair to say, it's a sort of new research direction in nuclear physics, which is leading to a lot of interesting things. And I will try to present some of the motivation of this and the progress, what we have achieved and what would be nice to do in future. So the outline of this talk is the following. I will review very shortly what are ultra-relativistic nuclear collisions and why we do them and what we study there. And then why is our nuclear structure becomes sort of inevitably connected with the with this field, and why we need to understand well nuclear structure to model well or equally well collisions of nuclei at high energy. And then I will discuss the milestone results at the interface. So what we have been able to understand. This involves also a lot of new experimental measurements, because that's actually what is driving, as I will show, all this research. And then if I have time, hopefully also I will discuss about prospects of new research, which I think can be carried out in the near future at the intersection of these two areas again. So starting then, ultra-relativistic nuclear collisions. So the motivation of ultra-relativistic nuclear collision is to basically looking for emergent descriptions of collective description of matter. So these are key to understanding physical phenomena across a wide spectrum of scales. You can understand the behavior of matter on galactic scales down to our scale. So this would be the Neckar River in Heidelberg, where I am, and also down to nuclear scales. The idea of using emergent collective description of matter, a prime example of it is hydrodynamics, is really powerful and allows you to understand nature in a very beautiful way. So on nuclear scales, one such phenomenon which occurs is the so-called quark-gluon plasma, which is what I focus on, and is what it is created in the collisions of nuclei. So we cannot observe it like the river, or we cannot take images of it with directly taking images with telescopes like we do for galactic structures. But this is so a model reconstruction of what is created in the collisions of nuclei at high energy, and we really trust it in the sense this is a temperature map with some structures which we trust a lot, and so try to convince you that this is true. So then just to tell you, so how to do this, you need colliders, very big colliders. So the most efficient way to reproduce this state of high temperature QCD matter is by smashing nuclei at the highest possible energies. There's a relativistic avion collider on Long Island in New York, which has done this for 20 years, is dedicated to doing this. And there also then 10 years later started the Large Hadron Collider, which does this about a month a year. there's the big ALICE collaboration, which is devoted to more like nuclear physics studies. So they study, they're more, it's a big collaboration which is looking precisely into collisions of nuclei. So then just to give you, let's say, a bit more of what we can assess by means of ultra-realistic heavy ion collisions. So this is a sketch of a collision. So these are two nuclei overlapping in the plane of the interaction. And then this famous quark-gluon plasma is formed. If you like, temperature is of order of trillion Kelvin. This is basically the state of the early universe, few microseconds after the Big Bang. Then this will evolve into disintegrate into particles which we detect. So we have this is just to give you some like things that the theoretical community likes to do in this field. So this is the only type of relativistic fluid you can create in a laboratory. So you can discuss about this in terms of energy, pressures, velocities, and things that are from the framework of hydrodynamics. Then being a fluid, you also need an equation of state. So this is the only fluid that you can produce in a laboratory which has actually the equation of state predicted by lattice QCD at high temperatures. This is very well understood from the experimental data. And then there's also other properties of this medium, like the viscosity. So this is not a perfectly ideal fluid, but there are like shear viscosity, bulk viscosity, these bulk properties which are coming from the underlying QCD and which we would like to extract from the experimental measurements. So you want to understand bulk properties of QCD matter in the high temperature regime of the phase diagram, if you like. And to do this, you have to collide nuclei and look for this quark-gluon plasma that is formed. So now the question is then about reconstructing information. So all I'm going to talk about is reconstructing information. The point is the following. You start with this guy which exists on scales on the Fermi scale. So this is like nuclear size, right? And then it expands. It's a very fast expansion. The temperature goes down as it expands, and then it disintegrates into particles. At time equal infinity, you only see a spectrum of particles which eventually survive to the detector. So that's all you observe, right? But then if you want to reconstruct the physics of the dynamics, which is here, this object, then you have to be able to reconstruct information from the experimental measurements, okay? And the way we do this is by means of so-called event-by-event analysis. This is an extremely powerful technique, which is, I would say, one of the salient thing of the heavy ion high energy heavy ion program is precisely the development of all these event-by-event techniques. And what this means is that in each collision, basically, we want distinguishes discerns a typical high energy like proton-proton collision where you look at a few particles that are emitted, to what you look into when you collide nuclei is that you look at a lot of particles which are emitted, like there are thousands of them. So this is a snapshot of one recorded event at the star detector at RIC. There are thousands of hadrons which are collected by colliding gold nuclei. And then you construct a spectrum for an individual event with a certain total number of particles, if you like. And then you can actually, in every collision, you can reconstruct this and then construct quantities like the average momentum of these particles, okay, which will tell you whether this expansion is very explosive or not. So this momentum quantifies the explosiveness of the expansion. Or you can actually scan over this angle and then try to calculate the Fourier anisotropies. You do an azimuthal decomposition of this distribution of particles and look for Fourier harmonics. So these are called VNs, that's the notation. So elliptic flow is called V2, the second harmonic is called elliptic flow and quantifies how elliptical this distribution of particles is. And triangular flow quantifies how triangular and so on. So you can do, basically this is the most important things that we like to do. We check how explosive the expansion is with the mean momentum, and also how, let's say, azimuthally asymmetric the distribution of particles is by means of these V2 and V3 coefficients. And this we can do basically, in a sense, in every single collisions, event by event. This is how we call it. An important thing that then we have to understand that. So by means of these things, we can actually reconstruct the information from about the initial state of the collisions, as I was saying, because in fact, what we see in the final states reflects largely the properties of the initial state. Okay, so let's call R the size of your quark-gluon plasma. So this is something we like to reconstruct from the particle distributions. Okay, you cannot measure the size of the quark-gluon plasma from your data directly. So what you know is that hydrodynamics, which is the appropriate description for a quark-gluon plasma, will generate a flow which is proportional to pressure gradients in your systems. And pressure gradients are things that just by dimensional analysis scale like inverse sizes, which means that if you take two systems which are of different size, like these two, then one will experience a stronger gradient because it's smaller than the other one, which has a weaker gradient because it has a larger size. So now if I do an event-by-event analysis, like a theoretical calculation, I simulate 1,000 collisions, and then I look at this at some impact parameter, then I look at the size of the quark-gluon plasma which is produced. This can fluctuate. It has a distribution, like can fluctuate by like plus or minus 10% around some mean value or something like this. And precisely because of this relation, then a system which has a small r, like here, will have a stronger gradient and will produce in the final state particles with a higher momentum, whereas a system with a larger size has a lower gradient according to this formula, and so will produce in the final state particles that are at lower momentum, where the momentum is measured at the end of the simulations. So what you see is that if I do 1,000 collisions and then I look at the momentum in the final state, what I'm actually measuring is a distribution of initial sizes of the system. So you see this very strong linear correlation is something that comes out of simulations and tells you that you're reconstructing information about the initial condition, in particular the size, from the distribution of average momenta. And the same is for the Fourier harmonics that I discussed. So if you have a system which has initially some anisotropic geometry, and this happens, for instance, if the two nuclei are colliding, in an off-centered way, such that the overlap area is elliptical. Again, the flow will follow a gradient, which is 1 over inverse size. So you have a larger size in this direction than in this direction for this distribution of density. So the system will flow more along this direction than along this one. So once you go to the final state, the momentum distribution will have some elliptic flow, because it will produce more momentum along this direction. So this is now momentum, than along this direction. And to somehow see this, in fact, the most convincing thing is to look at the experimental data. If you do collisions, these are lead-lead collisions done by the Alice collaboration, and you scan over the centrality variable, which at 0 tells you that these nuclei are sort of head-on and colliding in creating a circular interaction region. As you increase centrality, you go to more peripheral collisions where you have an elliptical shape. Then you measure this V2. You can see this phenomenon actually happening. So the V2 is increasing like dramatically as you make the system more and more elliptical. So this is a direct verification of this pressure gradient paradigm, which is just telling you that from this quantity, you can measure a property of the initial condition, which is the elliptical shape. So this is basically my bottom line for the interaction of collisions, which is that hydrodynamics is, so we do event-by-event analysis. We study momenta and azimuthal harmonics of the particle distributions. And these are because of the inherent features of hydrodynamics is something which they carry information about the initial system. And so this is why we can use this type of measurements to reconstruct information about the quark-gluon plasma that is created right after the collisions. And these are extremely powerful techniques, and this is how we made this field quantitative. Like we can, I can show you a plot like this one, right? And I really trust it. Like I trust these shapes, I trust the range of temperatures and how this evolves, okay? Very good. So in this business, then I reconstruct information about the initial conditions from the final state information. So why then I need nuclear structure, okay? So this is maybe now the most important part in a sense, which is the following. Now, consider a collision of two nuclei at high energy. So this is actually how it will look like at Large Hadron Collider, because there is a strong Lorentz contraction, which will make them entirely flat. So the relevant collision actually is in the plane orthogonal to the beam axis, if you like, x and y. Now, what this collision happens on an ultra-fast time scale, okay? It's about 0.01 Fermi, which would be like 10 to the minus 26 seconds at LHC, where a trick where they have lower energy will be like 10 to the minus 25 seconds. And this time scale is, of course, faster than any dynamics which is inside of any phenomenon within the colliding nuclei or anything. So then what we actually figured out from the experimental measurements is that the right picture to describe these things is that the collision is actually taking a snapshot, like an instantaneous photograph, if you like, of what is inside this nuclei and where whatever is inside this nuclei is located at the time of interaction. So this is actually a true understanding of how this collision takes place. So this is a picture which was not really anticipated, but became sort of evident from the experimental measurements, that in every single collision, you are basically sampling the content of the nuclei and constructing an interaction region from nucleon-nucleon interactions, if you like. And then what you can see is that in a realistic simulation, if I create my quark-gluon plasma out of this interaction region, I'm just really converting the geometry that is produced here into a distribution of density, which has the same geometry at the end of the day. You can really see this and just put it here if you like. And so this picture then naturally somehow makes nuclear structure become an important part of our problem. Okay, so this is really one of the important points. You just resolve everything which is inside this nuclei on a collision by collision basis, and this is what actually dominates the fluctuations of the geometry of the quark-gluon plasma in every collision. But then, I mean, and this is maybe the most important slide, you can understand these processes as follows. So if I start from a distribution of nucleons which interact in the interaction region, then I form my hydrodynamic quark-gluon plasma, which then flows to the detector by disintegrating into particles. So I can measure particles and construct observables from that. Okay, so I can do what we use are these event-by-event techniques, and we construct multi-particle correlations to actually make observables that you can compare to experimental measurements. So there will be an average transverse momentum in a number of collisions or events. This is why they call it EV. And otherwise, I can construct an mean squared anisotropy. So these are my Fourier harmonics of the distributions, and I can compute basically the magnitude squared by means of a two-particle correlation in the final state, or I can construct a correlation between the mean PT, the average momentum, and the anisotropy with a three-particle correlation. So this is a correlation of momentum and azimuthal angles. So you can see that these are basically the observables that we use in high-energy collisions. So I can give you a number of collisions where we have measured a number of PTs, momenta of particles, and azimuthal angles of these particles. And then you can construct these either one particle or two particle or three particle correlations. And these are the observables that you want to reproduce in the theory computations. But if you actually then try to look into, okay, what is the origin of these things in the frameworks of hydrodynamics, in fact, you can really see that this will probe because of this picture where you need to sample basically the wave function of your nuclei. This will actually probe directly, let's say, many body densities of your nuclear system. So if I define some particle density for the nucleus, like a psi squared, okay, and then I can define 1, 2, and 3 body densities, like by integrating out coordinates except 1 or except 2 or except 3. And these are the objects that I will be probing by means of these multi-particle correlation observables. Okay, so the input I need from nuclear structure is something which will tell me where the nucleons are, and also all their correlations, because this is what I will probe. So this is maybe the most important one, to nucleon correlation. I need this information from nuclear structure. Okay, this is what the observables at high energy probe. So how can I do this? How can I then? The nuclear structure is not a fully solved field, so they cannot just tell me, okay, take the wave function and sample it, because then I know all the A-body correlations. This is not something you can really get so easily. So we have to come up with more effective ways of doing that. So how do I create this picture for a simulation of high energy collisions? So for this picture, you actually need just two ingredients. One is a radial profile for your nucleus. And then the other thing is to know how many nucleons are in each nucleus, okay? So this is an example for lead. So lead is well approximated by a spherical, one-body density, if you like. We typically use this two-parameter Fermi function or Wood-Saxon distributions with some radius and some diffuseness. Then once I know what are the profiles for the protons and for the neutrons, I can just say, okay, in a collision, I just do a sort of mean field, calculation where I sample nucleus A and nucleus B from this distribution, and then I create my quark-gluon plasma from there. Okay, so the only information here is about the number of nucleons and the profile of the nuclei that we are colliding, and then I can play this game of sampling nucleons and create my quark-gluon plasma from there. So this is a very powerful thing and works well for nuclei for which this thing is the spherical approximation for this density plus a mean field approximation is appropriate. But the problem is that as years passed, we didn't only collide like we started to collide many more and more species. So we basically had at the beginning just lead and gold, and for this nuclei, a spherical approximation is good enough that you can sort of forget about the details of the nucleon distributions. But then now we have collisions for all these other species. And then now we sort of end up in some trouble because for uranium, this is very famous. It has a very nice prolet shape. This means that correlations on top of the simple spherical nucleus picture must be taken into account in our calculations. Okay, so I'll talk about this in more detail. So but the point here is just that as we have more species, and then we know that these species show non-trivial patterns of correlations and shapes across the nuclear chart, then we need to have a precise knowledge of what we are colliding in order to make meaningful comparisons and with the experimental measurements. So this is like what has mainly triggered work in this direction, that there are more experiments with more species colliding. So how do we implement then spatial correlations for nuclei that require that? We resort to the tool of deformations. This is what I would like to talk about. So we know from low energy nuclear experiments that a very powerful approximation for describing certain nuclei is by coming up with some intrinsic nuclear shape, typically an ellipsoid. And what this shape does is precisely that it allows you to encapsulate the effect of spatial correlations of nucleons, which are non-trivial. So if I take so how do you get some like two-body correlations from this? If you start with some intrinsic density of matter, which is deformed in some intrinsic body frame, then you will say, okay, a physical one-body density would be obtained as an average over all possible orientation of this object, which would be again spherical, so an average over Euler angles if you like. So then if I take the same distribution of matter and ask, okay, what are the correlations in this? So what is the two-body density? So what I would like to do is to rotate it, so omega, and then compute at 2 points, and then again do the average over orientation. But what happens is that unless the density is spherical, this object will not be equal to the product of two of these. So this means that with this picture of intrinsic nuclear shapes, you can actually produce correlations which are consistent with your data. And for me, it's a sort of definition of what a deformation is an enhancement of correlations, in particular to body correlations, which is can be captured by means of this deformed shape picture. And so this is an effective way of implementing correlations for nuclei, and this is what we have used mainly. And I can immediately show you what this does at the level of our simulations, right? So now, let's say, I can show you why this is so important. So let's take a collision of two nuclei which is oriented in this way. Then what this will produce is a quark-gluon plasma in the plane, of the collision, which is very elliptical. So this would be like a uranium-uranium collision with nuclei oriented in this way. Or you can do the same collision with nuclei oriented in this way, but this time you will have a system which here will look like circular. Okay, so this is just an obvious consequence. And what happens then, if you look at more like observable quantities, is that this is a system which has, on average, has a lower energy density. So it will produce particles with the lower momentum, if you like, once it expands. Whereas this system has a higher energy density on average, and so it will produce parts. So this we call tip-tip, will produce particles with a higher momentum to the final state. And if you look at the V2, which quantifies the elliptical deformation of the interaction region, so the elliptic flow, so this will be much bigger. Actually, it's a factor 3 in this extreme case, in this situation, a body-body collision, than in this situation of a tip-tip collision. So you see that these shapes will leave like dramatic, and a dramatic impact can leave a dramatic impact on the geometry of the quark-gluon plasma and the subsequent collective flow. And this is why we need to implement them and be careful with that for quantitative studies. So I would like to recap this first part, which was like theory introduction. So relativistic collisions of nuclei form a quark-gluon plasma that behaves like a fluid. And if you measure average momenta and Fourier anisotropies, like elliptic flow, what you probe is the geometry of the initial state of this QGP. So you can reconstruct that information from the data. But then this geometry is actually something coming from nuclear structure, most of it. because what we understand now is that these collisions provide a snapshot of the content of the colliding nuclei. So you need to know where all the nucleons are located at the time of interaction. And so the spatial distribution of nucleons are really crucial to model these collisions, okay? What we probe are basically all spatial correlations of this nuclei, so all the many-body physics is probed by the collisions. And crucial, we have now a significant pool of species which has been used in these high-energy experiments, so that we really needed to go and talk with the nuclear structure community to get more and more precise inputs for a large variety of nuclei, which exhibit, as I will show you, deformations and lots of non-trivial things. So then the next part is about milestones. So I call them milestones, but basically the main, I would say the main results of what we have made progress with and understood in the past 3 years. So the first thing I would like to say is that we have basically streamlined a workflow, if you like, for inputting energy density functional calculations of low energy nuclear structure to simulations of high energy nuclear collisions. So what we do, and here particular credit goes to people from the French community like Benjamin Bali or Michel Benda, where so they can actually do state-of-the-art mean field and beyond mean field calculations of nuclear structures. So these are nuclei which are interesting for me: lead, gold, xenon-129. So they can study like basically potential energy surfaces, if you like, and see where minimal light, where the ground states are. So they will tell me, okay, I see these deformations in my calculations. Then what they do, and this is something that is in advance, is that we compute one-body densities from these mean field states. So we have some mean field states which are constrained to these deformations, depending on the nucleus. And we can calculate a one-body density from that, so distribution of matter, if you like, of A particles. And then what we do typically is we take this result and we fit it with some simpler function that we can parameterize in terms of standard, like surface deformation coefficients, like beta-2, gamma for the triaxiality, beta-3, beta-4 even. And then this will be basically the object that you use in the simulations of high energy collisions, okay? So this is your particle density. You will say, okay, every collision probes an orientation for this deformed shape, and you will do your sampling of nucleons from that and try to see what the problem plasma look like and what you get from that. So the first thing then is, for instance, the intrinsic shape of uranium-238. So this is a beautiful example because it shows you that, in fact, this prescription of computing this one-body density from density functional theory is really crucial. Because one question you can ask is, okay, how do you take the deformation coefficients for your simulations, okay? And so in the past, we were actually doing this in a rather naive way. So we were taking like information from low energy nuclear physics for this beta coefficient related to the measured, spectroscopic information, B2 moments, etc. But in fact, now we have these calculations done by Wouter Ristens from Brussels. What we need is not really that for heavy ion collisions. So if you have a certain quadruple moment for your nucleus corresponding to some B2 value, and this will be a beta of about 0.29 for uranium, which is this red point. So these are 20 Skyrm density functional calculations. If you actually compute this one-body density and then fit a Woods-Saxon distribution like this one, the beta coefficient is no longer 0.29, but is closer to 0.25 for all of these calculations. So this is just the conversion from, let's say, if you want a volume deformation and the surface deformation. But what is important is that these things matter a lot for us. So what the STAR collaboration at RIC has measured is that there is an enhancement in the elliptic flow of uranium collision compared to gold-gold collisions. So this is this data, which is about 1.5. So this is the experimental data. So if we do theoretical simulations with this naive value taken from BE2 value tables, then we get this very large number for the hydrodynamic calculations, which overshoots the data. Whereas if I take the results from the fit of a proper one-body density from DFT, I get this 0.25, and this actually reduces a lot of the signal and makes it, in this case, closer to the experimental data points. So this means that we have sort of even evidence that we really probe these one-body densities, which are the relevant objects for heavy ion collisions. And they're not really something that you can measure at low energy, but you have to take some low energy, let's say some low energy model, which is tuned to low energy data, and then convert that into information that you can use to simulate the collisions. So this is how it should be done. Then a second advance is that not only we see these shapes, but we have even been able to make techniques to discern whether the nuclei are oriented in this way or in this way. This is the cartoon that I just showed you. So you have these body-body collisions which create an elliptical thing. And these tip-tip collisions will create a circular things. As I discussed previously, there will be opposite effects on the V2, on the elliptic flow and the momentum outgoing particles. So elliptical means large V2, circular means lower V2, but this has more energy in it, so more momentum, whereas this has less momentum because it's sort of more dilute. So what was actually measured by STAR, actually this paper appeared today on the archive. So they actually said, okay, let's take collisions with a sort of very central, like this one that I'm showing, like it's very small impact parameters. And then we make a scan. We measure the ellipticity as a function of the PT. And they precisely see this effect that as you make it more elliptical, the PT goes down. So you decrease the average momentum of the measured particles, but their distribution becomes more elliptical. Conversely, if you look at particles with higher momentum, their distribution is more circular, which is verifying the simple picture I'm showing in this plot. So we can actually, to some extent, discern different orientations by means of this kind of experimental techniques. Now, a step forward to this is that then you can actually move from prolet to triaxial nuclei. So triaxiality, just to recall you, is the imbalance of the length of the axis in your ellipsoid. So prolet will be two short axes and one long. Oblet is two long and one short. Triaxial is three different. And the triaxiality, in fact, impacts this correlation between the ellipticity overlap area and the momentum of the particles. Just the picture is really just this, that if you look at collisions which will produce a low momentum of particles, so a prolet nucleus as an elliptical shape, an oblet nucleus as a circular shape, and then this will be visible in your data. So we did simulations for different, so these are xenon and lead collisions. We did simulations of an observable, which is basically, again, the correlation between this V2 and the momentum of the particles, and we scanned over values of the triaxiality of the xenon nucleus. We can clearly see a signal from different values of the gamma, and then this was measured experimentally by the Atlas collaborations, and we were able to actually somehow say that the scenario with the triaxial xenon, which is actually what is predicted by Li et al. And low energy nuclear structure, is favored by the LHC data. And just as a bonus here, what we also understood is that this triaxiality is actually, if you try to understand the observables that you are measuring, again, this correlation between a momentum and an azimuthal anisotropy, is something which probes like to leading order the three-body density in the nucleus, which is, I think, is an interesting result, and we still have to understand this better. So we can see the shapes, we can see the triaxiality of the shapes even, and then we can see even more. So let me just go to 2021. These experiments were performed at RIC. So these are called isobar collisions. You do ruthenium and zirconium collisions. So these are isobars. So the ruthenium has the same number of nucleons as zirconium. And what you expect, or at least what we were expecting to some extent, is that if you take observables between this system and these systems, they should be basically identical. So let's suppose you measure some observables in ruthenium collisions, then you divide it by the same observable in zirconium collisions. The baseline is unity. And if you don't measure unity, this means that there is some difference in the structure of the colliding nuclei. So this was not done to search for nuclear structure effect, but eventually this is what they did. And we don't have to discuss why they did these experiments, but eventually they end up with very precise measurements of nuclear structure. And this is one example. Okay, so this is precisely this ratio of observables. So I'm showing you now STAR preliminary data, where they look again as the elliptic anisotropy, the elliptic distribution of the elliptic anisotropy of the particle distribution taken between. They make a ratio between ruthenium and zirconium collisions, and they see an enhancement compared to unity. Now, in fact, if you just do simple theoretical calculations and arguments, you can actually convince yourself that the elliptic flow that they measure is just something which has like a baseline that you would have for spherical nuclei, and a correction which comes from the quadrupole deformation, such that when you take a ratio between two systems, since the systems are isobars, the baseline for the ratio becomes unity, which would be this line, and then this will be enhanced or depleted basically by the relative quadrupole deformation of these two species. This is just a theory expansion, basically. Now, if you look at low energy nuclear physics knowledge, it is clear that ruthenium should have a larger deformation than zirconium. And this is precisely consistent with what is observed by STAR, which is observed an enhancement of the elliptic flow in ruthenium-ruthenium collisions. So this numerator compared to the zirconium collisions, because zirconium nuclei are very, very spherical in the ground state. But then you see that they measure also another thing, which is called V3, which is basically the triangular deformation that I introduced at the very beginning of the particle distributions. And this you can actually show that the baseline for the ratio of the triangular flow is unity, but then is corrected by the octuple deformation of the nuclei. So once we see that there is this depletion from unity, meaning that zirconium has a higher triangular deformation, if you like, than ruthenium, then this must imply for us that zirconium has a higher octuple deformation than ruthenium. Okay, so this data basically is telling you that. So there is some ellipsoidal shape of zirconium, octuple shape of zirconium, which has played some role. So then if you look at low energy information, this is not so clear what is going on. So there is in fact data for like low-lying 3- state of zirconium, which is actually one of the lowest in the nuclear chart and implies a strong octuple collectivity, although there are no theoretical predictions for what a beta 3 would be, because this is still in a sense too difficult for energy density function calculations. And about the ruthenium beta 3 is not really known experimentally, and again, very lack of knowledge from theoretical calculations. So this is now, we triggered new calculations. Hopefully we'll have more information in the future, maybe even from low energy experiments. But the picture for us is that we're clearly seeing an octuple deformation in zirconium, which is much larger than in ruthenium. Then, so this was more on the deformation side. So again, quadrupole, octuple, triaxiality, this is all very visible for us. But now we can go to smaller nuclei. And in particular, what is interesting for us are oxygen nuclei. So this is 16 oxygen. The interest here is that, again, the oxygen-oxygen collisions have even performed a trick. And so there was data which is coming out for these collisions, and then they will also be done at the LHC in 2025. So we need, again, nuclear structure knowledge about these systems to do simulations. So what's really great about oxygen is a nucleus which can be computed in so-called ab initio approaches of nuclear structure, and this has been done for the purpose of simulating heavy ion collisions. So we have two results from quantum Monte Carlo calculations. Basically, these are auxiliary field diffusion Monte Carlo simulations. These are done typically at Los Alamos. And otherwise, we have results from the nuclear lattice effective field theory calculations. And these two approaches are sort of similar in spirit. They start from some configuration of nucleons, and then they do some imaginary time evolution to reach the ground state. So what they actually can give us are configuration of nucleons in the ground state, which carry up to A-body correlations, which is, of course, great for us because that's what we would like to have. Otherwise, we have also recent developments from Saclay. This is the so-called newly developed ab initio projected generated coordinate method approach, which is, again, a sort of density functional, variational method, which gives us an intrinsic deformed density that we can use for oxygen collisions, but from, an ab initio interaction. So just to then flash some results, like the calculations from Los Alamos have been used in some theory papers where we compute the ellipticity of the QGP geometry in oxygen-oxygen collisions, and they tried to see what was the impact of the clustering correlation. So it correlated would be with clustering correlations from the ab initio computation, uniformly where they switch off some other correlations, and they were able to see like percent level correction to the geometry of the QGP, if you like. Then similar analysis was done for the nuclear lattice effective field theory configurations. So they had their full results, which is these triangles for the elliptic flow as a function of the collision centrality. And then we're testing against simpler models of nuclear structure to see whether the clustering correlations of the ab initio computation would be visible in the results. Again, they found some like percent level corrections. And then this is the calculation of Bali. It's the intrinsic, I'm very happy I can show you this actually. This is the intrinsic shape of oxygen from an ab initio calculation, which can then be used. It's an effective way of encapsulating basic correlations in terms of a deformed and clustered density, as you see. It's coming from Kyle-Lefty interactions. And we can also use that in ion collisions simulations, and this is a work in preparation. Final highlight of all of this story is that we have also recently figured out that these nuclear shapes and the same sort of picture of high energy scattering will play a role for the future electron-ion collider in gamma-mediated processes. And this, I just want to very briefly show you how this works, because it's a very nice story. So the process they were looking at, and this was done in this recent paper, is gamma nucleus collisions, so photon scattering of a nucleus, but at very high energy, what the photon does is actually splits into a QQ bar pair, which will be this thing. And then this impacts the nucleus, and you call T of B and the density of gluons in your nucleus, and then this is produced to the final state. So this QQ bar pair is produced as a final state, for instance, at the J psi, which is the particle they were interested in. So the scattering amplitude of this process is actually something that is proportional to the Fourier transform of the T of B. So it is like taking a diffraction, if you like, of the profile of your nucleus at the time of interaction, which would be this T of B. So when you take then a squared amplitude and you average to do like a cross section, something which is experimentally accessible, what you actually do is that you have to multiply two of these things to square the amplitude, and this again will basically involve a product of two coordinates in your nucleus, which will then assess the two-body density again of your nucleus. So what is actually the amplitude squared as a function of the conjugate variable, which is called T, which is basically conjugate to the relative distance between two coordinates in your nucleus, actually probes the two-body density of the nucleus, which means it will probe the deformations. So this is, the universality of this correlation effect. So I can do scattering of nuclei, high energy heavy ion collisions, and be sensitive to this. I can do gamma nucleus collisions. I'm sensitive to the same object. I will be sensitive to the spatial correlations, like the deformations. And this is like a precise calculation of this. So this is the resolution variable, the conjugated variable. Then you look at some cross-section, which probes this object. And you can see the calculations done depending on the deformation of the uranium nucleus. So the value of beta 2 actually depends, it impacts a lot your observable. Then they tried also to try an octuple deformation, an hexadecapole deformation. And it's interesting because different shapes, which are basically higher order of excitations as you increase the order of deformation, they impact different resolution scales, which is expected. Like higher resolution means you probe shorter distance scales, so like hexadecapole, whereas quadrupole is more like a more longer range effect. So this is then the end of my highlights. I would like to just recap them again. So we have established a workflow to input state-of-the-art density functional calculations in simulations of heavy ion collisions. We have clear evidence of the ellipsoidal shape of uranium-238 compared to the baseline of gold, which is much more spherical. Then we have also figured out techniques to discern orientations of the colliding ions. And thanks to that, we have also been able to see basically the impact of the full triaxial structure of xenon-129, which in our approach is basically a probe of the three-body density of the nucleus, which is a very, I think, interesting observation again. Then we have this technique of the isobar collisions is something which, as I showed, allows you to take two systems, take a ratio, and then see the departures from unity, which will indicate some nuclear structure effects. And this has clearly isolated the impact of the octuple deformation of zirconium, which is giving like a hard time to theorists on the low energy side, because it's something which is even difficult to predict in theory. Then we will have oxygen-oxygen collisions, which have enabled us to connect to ab initio calculations of nuclear structures, which is very spectacular, of course. And then finally, we have actually figured out that there are observables that will be measured in future electron-ion collisions, or if you like, even ultra-peripheral nucleus-nucleus collisions mediated by photons, which are also probing the many-body correlations in the nuclei, and so all these deformations. And again, we need solid input from nuclear structure for that. So this was the summary of highlights. The last part of my talk is prospects. So I think I'll take maybe 5 minutes or just a bit fast on this, but I just want to give you an idea of what would be interesting to do in the future. Now that we have established a connection with the low energy community and that we have figured out that so many things where that is important for us. So the first thing that I would like to do in future is to basically perform consistency checks of our understanding. So currently, we just have some picture of heavy ion collisions, and then we say, okay, let's take some low energy input that we can use in our simulations. But then the question is the following. Suppose I forget about the low energy input to a great extent, and I just take high energy data and try to reconstruct information about nuclear structure from that alone. So would I get a picture of the nuclei which is consistent with the low energy expectations? So can I do the sort of reverse engineering and make sure that the whole picture is consistent? So I think this is very relevant, and this is actually, we have an example where we have tried to do this, and I think successfully, which is the following. So we want to simulate lead-lead collisions, okay? So to do that, we need some distribution of matter, and this is basically given by some proton distribution plus some neutron distribution. Sorry for the strange normalization of these curves. So what we did is the following. So instead of just taking some low energy knowledge about this profile, we say, okay, the protons, that's known very well from low energy scattering, so we just trust that. But the neutron is not known so well. So we take the A, the diffuseness of the neutron distributions, will be this green curve, and we let it vary as a model parameter in our calculations, okay? So this is like, yeah, this is like the variation. And then what we do, we take the high energy data and try to reconstruct this A just from the LHC data, okay? And so this is basically, the way this can be done is by means of Bayesian analysis. I think this is a standard tool in both nuclear structure and now energy collisions. So we have some model, we have some experimental data, which will be the convolution of, observation, which will be some convolution of, if you want, theory information and data, and then we want to basically reconstruct the distribution of parameters of our models in the parameter space, which give somehow the description of the data which is the most consistent. Okay, so and what we've done then is that we were able to do this for the neutron skin, if you like, of the lead-208 from the LHC data. So we could extract the distribution of what is called a posterior distribution for this parameter, and also quantify, so this will be this delta RNP, so this is our extraction, and quantify how this is correlated with other parameters like PQW, which are parameters of the hydrodynamic model, which actually carry information about the high energy dynamics. So this is the first time where we actually have a correlation, if you want, between a feature of the high energy model and a feature of the colliding nuclei. And we were sort of happy with this because the number that we got, which is 0.217 like Fermi, with some uncertainty, is consistent with the low energy expectations, which are typically around 0.2. And even the uncertainty that we get from this theoretical extraction, like from doing a Bayesian analysis, Bayesian inference, is even competitive with some low energy estimates from experiments. So this was, I think, a successful attempt, but this we are able to actually at least try to reconstruct information about the nuclei just from the LHC data and without any quantitative input from nuclear structure. So can we do this then for more features? This is the goal, I guess, in the next 1 or 2 years. For instance, we should be able quite easily to take xenon data from LHC and say, okay, we have data for something which probes the quadrupole deformation, which is basically the elliptic flow, and something which probes as well the triaxiality. This is what I showed you before, this rho elliptic flow momentum correlation. And so we should be able to actually do a Bayesian analysis again and extract beta and gamma of xenon from LHC data and then see if that matches, again, the information from low energy physics. And this will be extremely important. The second prospect I have is about proposal for future runs. Just to tell you, heavy ion collisions will be done at LHC, for instance, until the very end of the running of the machine. So currently we are in so-called run 3, 2024. Oxygen-oxygen collisions will be run in 2025. Then 2029 there will be run 4, where it's possible that perhaps some other species will be collided. And then run 5, which will be one of the last ones, the program is still to be decided in a sense. At the same time, the electron-ion collider would start. So there will be more, high energy experiments with nuclei. And what we would like to basically tell the community is what would be interesting to do, or if you want to make proposals, like what would be interesting to propose. Okay. So one thing, for instance, is light nuclei. Again, it's very nice because we can have calculations from the ab initio people, ab initio calculations of nuclear structure. So these are actually state-of-the-art calculations for nuclei as I add basically an alpha particle to carbon, if you like. So these are ground state shapes that are derived in different theories. Ab initio no Corshell model, nuclear lattice effective field theory simulations, again, projected coordinate method ab initio from Saclay. This is carbon, oxygen, and neon. So this kind of very, accurate inputs, we would really like to use them in simulations. And one case I just want to mention is that of neon. There is a paper which will shortly appear on the archive, which is a collaboration between basically us. These are the green heavy ion physicists, the people from Saclay working on generated coordinate method, red, and the people from the nuclear lattice effective field theory, which are in blue, which is about exploiting neon to do basically high energy physics. So this is neon compared to oxygen. This is a very nice, what we call a bowling pin shape, which we want to, we can actually use to do something useful for the high energy program. And just to give you an idea, the interest in colliding these small nuclei is from the fact that we want to understand the limit of applicability of the hydrodynamic model of the QGP. And basically, if you make your system smaller and smaller, then the picture could break down when we want to understand whether it does or not. So it's very interesting to go to light nuclei for this reason. And what's very nice with neon is that you can exploit this shape that it has to basically see the enhancement of its elliptic flow compared to the oxygen baseline. And so this is something that we see here. So this is basically a ratio of elliptic flows taken between neon and oxygen collisions. This becomes as large as 1.2. Which means that by means of this bowling pin, which is a very elongated structure which impacts our elliptic flow, we are able to generate geometry-induced effects and test very effectively the hydrodynamic paradigm, also in collisions of these light ions, where we would still like to understand if this emergent description of QCD matter is appropriate or not. So this is a very nice way of exploiting this bowling pin to do high energy physics, if you like. So then the natural question is, what are other interesting cases? I've just shown one. So there are many which have been discussed. Now people are bringing up things like calcium-48 is also discussed a lot in the context of neutron skins at low energy. So it would be interesting to try to determine that at high energy. Otherwise, is there anything relevant from knowing precisely deformations about the nuclei which are used for neutrino-less double beta decay searches? So these are pairs of isobars, so they're ideal actually for us. So there were recently people from Japan bringing up that it would be interesting to study the small triaxiality of rare earth nuclei. So these are nuclei that are very deformed and very slightly triaxial. So community discussions will take place this year and the next, I guess, to make suggestions. Basically, if we want to do things that are interesting both at high energy, but that could also maximize the scientific output with something which would be interesting as well at low energy. So what should we propose? So these are the kind of things that we would like to do. So okay, I took a lot of time, but so my last point, maybe just flash it, is that the way I see it, the heavy ion collisions are giving us somehow now taking the other side of the question. Heavy ion collisions are giving us a new way to assess experimentally correlations in nuclei in particular. This is extremely powerful, apparently. And so the question is whether there is complementarity between the information that you get again at high energy and that you get at low energy, and whether we could try to study in theory what this complementarity is. So what I see is that the two fields have gone rather quite close in terms of techniques that are used. So I see that there are now Bayesian analyses of low energy nuclear structure, where you try to reconstruct all of the parameters of your chiral EFT from some set of data. And this is also what we try to do at high energy. So we have a multi-parameter hydrodynamic model, a set of parameters that we want to reconstruct on the data. And what people I see they're doing are so-called global sensitivity analysis. So I can give you an example from my energy. So this is a parameter that you would like to reconstruct on the data. It's called the bulk viscosity of the quark-gluon plasma. And this is how this parameter impacts various observables that you can measure at high energy. So this is what they call a global analysis, if you like. And a similar thing was done in the low energy context. So they take some observable at low energy. So this R42 is the ratio of this E4 over E2, which quantifies somehow the rigid rotor behavior of your nucleus. This was done for 3 nuclei. And this basically they wanted to see how this observable is determined in terms of parameters of the EFT. So the deformation of neon, for instance, what are the parameters of the EFT which actually determine it? So there are a few which carry the strongest sensitivity. And the question for me would be, okay, suppose I replace now the low energy observable with some high energy observable like V2 by elliptic flow again. So is elliptic flow generated by the same kind of nuclear structure information, or does it probe other parameters in this chart? So in a sense, if I want to reconstruct this, for instance, the low energy interaction, is the information coming from my elliptic flow or the information coming from this R42? Are they complementary? And this is, I think, this can be actually studied in theory. So this would be a sort of long-term theoretical goal. In general, again, just to tell you, if the collider were used to collide many more species, you will generate an infinite amount of information about the correlations of the systems. And so this would definitely, I think, add new constraints to nuclear structure as well. So this, again, just to see the question from the other side. Okay, so one dream or one thing we like to propose, again, is the samarium chain, for instance, which is really beautiful. It starts from a spherical nucleus and then goes into a very well-deformed nucleus along an isotope chain. It will be really spectacular to see this, for instance, in high-energy experiments. I can finish. Sorry if it's to take a bit more time than 45 minutes. Just my conclusion is really straightforward, okay? I just, again, show you this picture. We measure multi-particle correlations in the final state of heavy ion collisions, and we can relate that to many body correlations in the colliding nuclei in a very effective fashion. Therefore, if we want to understand high-energy data for collisions of many species, we need a very precise knowledge of the structure of the collided nuclei. But at the same time, and this, and then I will discuss all the progress made in that direction. At the same time, this is actually experimental data which carry information about these correlations. So how are these two tools complementary even to understand, in general, emergent property of QCT matter? So I think there will be a lot of further progress and collaborations in future, and I'm really looking forward to. Thanks a lot for listening. I hope this was interesting.